Hey everybody, Mr. Judson here. So we had so much fun reading the other day that we're gonna do a little more reading. So this is in Chapter 1, Section 5. We all know what a vertical asymptote is, but just in case you forgot, I've got a reminder here. It says this, it says let f and g be continuous on an open interval containing c. All right, we know what continuous means. If f of c does not equal 0, and g of c does equal 0, and there exists an open interval containing c such that g of x does not equal 0 for all x not equal to c in the interval, then the graph of the function h of x equals f of x over g of x has a vertical asymptote at x equals c. Well, duh. Of course it does. And there's a proof in Appendix A if you want to take a look at it. Oh my gosh. What did they just say? Well, let's break this apart slowly, kind of like we did last time. So let f of g, so my first question is what's f and what's g? Okay, it's a fraction, numerator, denominator. Let f and g be continuous on the open interval containing c. So it doesn't have to be continuous everywhere, it's just on an open interval. So open means we've got parentheses. So let's say between 2 and 4, there's an open interval and this function's continuous there. We're talking about some c value between 2 and 4, okay? Or whatever, I'm just making up numbers here. So let this numerator and denominator be continuous functions on an open interval which happens to contain c. And if f of c does not equal 0, so f is the numerator, it means when we plug that number in, we're not going to get 0 here. And g of c does equal 0. So we do get 0 in the denominator. The reason we don't want to get 0 in both is that's when you have like the same factor top and bottom and you get a hole in the graph. Okay? So we got to make sure the numerator does not equal 0, but the denominator does. And there exists an open interval containing c such that g of x does not equal 0 for all x values in c. Okay, so everywhere else on this interval, that denominator does not equal 0. Only at c. Okay? They're saying g of x does not equal 0 when x does not equal c. That just means everywhere else. Well, so that means my denominator equals 0 at c, but not anywhere else. Therefore, there's a vertical asymptote at x equals c. So I think what they just said is if the denominator equals 0, you get a vertical asymptote. Unless there's a hole in the graph. Which I think we already knew that. So they're not really telling us anything new here. They're just trying to write this down in some fancy mathematical way. So anyway, that's one of the things that we want to talk about today is finding asymptotes. And what we learned last year in pre-calculus is still the same thing. Asymptotes happen when your denominator equals 0, but the numerator doesn't. Okay, if they both equal 0, then there's a hole in the graph at that point. All right, so we're going to have some questions where they'll give us a function, f of x equals x squared plus 2x minus 8 over x squared minus 4. And what they want us to do is to tell them, are there any vertical asymptotes or removable discontinuities? A removable discontinuity means we've got a place where this function is discontinuous, but we can remove it by canceling those factors. Okay? So I think the first thing I want to do here is factor this expression. So if I factor the numerator, I'd have x times x. Two numbers you multiply to get 8 and subtract to get 2. Positive 4, negative 2. And if I factor this, I've got x plus 2 times x minus 2. So if we go back and look at our theorem here about vertical asymptotes, when they said that f of c does not equal 0 and g of c does equal 0, right? Well, here's a spot where they both equal 0, at 2. That's not where there's a vertical asymptote, right? What we learned last year is we can cancel those, and there's a hole in the graph at x equals 2, and that is considered a removable discontinuity. Now, does that mean that the hole doesn't exist? No, it does. But what we can do is we can create a piecewise function where we put a point right where the hole's at. Okay, and I'll show you what that looks like at the end here. All right, so I've canceled that. There's no asymptote there because both numerator and denominator would equal 0 at 2. Here, at negative 2, we get 0 in the denominator, but not the numerator. And so there's a vertical asymptote at x equals negative 2. And a removable discontinuity at x equals 2. So how do we remove this? Well, we would say this. F of x equals a piecewise function, and what it equals is x plus 4 over x plus 2 if x does not equal 2, because that's where the removable discontinuity is. And what does it equal if x equals 2? Well, we're going to plug that 2 back into here, and we'll get 6 over 4, which reduces down to 3/2. That's where the hole was at 2 comma 3/2. This would be our y value. Okay? And so going back to the original function, we're saying that that function would equal this. It looks like this, as long as x doesn't equal 2. But we're going to fill in the hole with this point right here, 2 comma 3/2, and that will remove that discontinuity. All right? You guys don't have to write this stuff down. We just have to say, where is that removable discontinuity at? All right, let's try another one. All right, so we want to be able to find all asymptotes for this function. You guys go ahead and give it a shot. All right, so I got to factor it first. So I think I'll start with the numerator here, and I'm going to factor a 4 out of each of those. Left with x squared plus x minus 6. Here I'm going to factor an x out of each of those. And so I've got x cubed minus 2x squared minus 9x plus 18. And so now I've got to factor that, so I've got 4 times, let's see, x plus 3 times x minus 2. That'll give me a negative 6 here, and 3x minus 2x, that'll give me a positive x in the middle. This I'm going to have to factor either by doing factoring by grouping or synthetic division. And I think I'm just going to do synthetic division. It's not that that's the best way, it's just, I don't know. I'm just going to go with that. So I'm just going to go off to the side here. I'm going to go, okay, my coefficients are 1, negative 2, negative 9, and 18. And those do not add up to 0, so I'm not going to try 1. So I think the next one I'll try is 2. Bring that down, multiply and add, I get 0. Multiply and add, I get negative 9. And then a negative 18 plus 18 is 0. So I got lucky, I found one right away. So that means that this factor is going to be x minus 2. And here I've got x squared minus 9. And so now I know that's x plus 3 and x minus 3. So here are my factors. I had this x to begin with, and then x plus 2, no, minus 2, and then x plus 3 times x minus 3. All right, so removable discontinuity at x equals negative 3. They didn't tell us to find that, but I can at least think that in my head. Here's another removable discontinuity at x equals 2. And so what I have now is 4 over x times x minus 3. And so there's going to be a vertical asymptote at x equals 0 or x equals 3. Now, this question said, find the asymptotes. I'm just going to assume that means all of them. So there's the vertical ones. What about horizontal asymptotes? We've got to think back to what we learned last year. Horizontal asymptotes, if the exponent in the numerator is less than the exponent in the denominator, then it's automatically at y equals 0. It's right on the x-axis. If these two exponents are equal to each other, then I look at the leading coefficients, right? And if this exponent is larger by 1, then there's a slant asymptote. Okay, but since that's smaller, we know that there's one at y equals 0. All right, so a horizontal asymptote at y equals 0. There's my asymptotes. All right, so that's one thing we want to do is just locate asymptotes. Really, this kind of fits into the idea of limits because, you know, what we're saying with a horizontal asymptote is as the limit goes off to infinity, the value of this function is going to be 0. And as it goes off to negative infinity, the value is going to be 0. As x gets close to 0 or 3, you know, we could have a situation like this where they both go off to infinity, or we could have a situation where one side goes to infinity, the other goes to negative infinity. Okay? But we still have this idea of, as we get really close to a number, what's happening to the y values. Okay? We're also going to see some other limits that may have infinity for answers. This chapter is really called Limits at Infinity, okay, or Limits of Infinity. All right, so we know there's an asymptote at 2 here, but they're asking us to find the limit as x approaches infinity from the larger side. So from the larger side, if there's an asymptote at 2, I don't know if it's going like this or like this, but it's probably going to be one of those. You guys go ahead and see if you can find that answer. So I think if I was doing this, I would just say, let's just make an xy table and plug in a number slightly larger than 2, 2.001, 0001. And so to do that, I need a calculator. All right, so I've got 2.0001 minus 3. And in the denominator, I've got 2.0001 minus 2. A negative 9,999. Now I already know if I graph this, there's going to be a vertical asymptote at x equals 2. So there's 2 right there. When I see this on my calculator, that tells me that we're going down towards negative numbers. Okay? So I know that this graph is going to look like this. Those exponents are the same. So you look at the leading coefficients. And at 1, we have a horizontal asymptote. So this graph should come up and get close to that. So numerically, I just found that my limit is negative infinity. Here, graphically, that would agree with that. And so there's my answer. Actually, I did it two different ways. Thinking about what I know from last year, vertical asymptote there. This is at 1 over 1, there's my horizontal asymptote. And I know when I plug in a number on this side, I got a negative answer, so it must be going down. Okay? All right, let's try another one. I've got the limit as x approaches 0 from the small side of 1 plus 1 over x. You guys try that and see what you get. All right, so if I just think to myself, y equals 1 over x plus 1, I'm thinking about last year, our basic functions of graphing. The center of the asymptotes would be at 0, comma 1. Okay? So if I was going to graph this, 0, comma 1 is going to be right here. I would have an asymptote that goes this way, one that goes this way, and I would have part of my graph right here and part of my graph right here. It's the rational function. Okay? This would be like saying x plus 0. That's why I said 0, comma 1. And so it looks to me like my answer as I get close to 0 from the negative side, this thing's going down to negative infinity. Right? So I think that's what the answer is. But if I want to just double check and make sure, make an XY table, do a numerical option. I don't think we have a real simple algebraic way to do this, although I'm going to give you something to think about here in just a minute. If I plug in a number approaching 0 but from the small side, that means a negative 0.0001. So I want to plug that in. So I'm going to have, clear this, so I've got 1 plus 1 divided by a negative 0.0001. Well, there we go, a big negative number again. That means we're going off to negative infinity. Okay, negative almost 10,000 is way down here somewhere. So I'm going to say that this is equal to a negative infinity. So here's another way to think about this. If I'm going to do 1 divided by a really small number, right? So 1 divided by 0.000001. The more zeros I put in there, the bigger this thing becomes, right? How many little tiny numbers are there in 1? If I'm dividing by 0.000001. How many of those little tiny numbers are there? There's a whole bunch, right? And since I'm approaching from the smaller side, I want to divide by a negative number. So 1 divided by a little tiny negative number is a very big negative number, or negative infinity. 1 minus infinity is negative infinity. So you can kind of think your way through this and get the answer that way. Problem is a lot of times as we think our way through things, we may not be thinking right? So I think having a couple things to look at that confirm your answer is a good thing. All right, so there's that one. If you wonder why are we doing this, a big part of calculus is being able to graph difficult equations using concepts of calculus. So last year we learned how to graph parabolas and square roots, and eventually we went to some rational functions that had factors in the numerator, factors in the denominator. So we had zeros and asymptotes. That helped us. But what if I just get something messy that I just don't know what it looks like, and I don't have a calculator available? We're going to have to do some calculus stuff, and part of it is finding those asymptotes and thinking what happens as you get close to them. Okay? All right, let's try one more problem. You guys see if you can find this limit. So anytime I see something like this, I'm always thinking about factoring first. Factor and cancel. Make the problem easy. So I'm going to rewrite this as the limit as x approaches a negative 1/2 from the larger side. And if I factor this, I know this could only be 1 times 1. If I try 3x and 2x, there's my 6x squared. I want to get 3x minus 2x to produce that term. So that's negative, that's positive, and we get our negative 1 in there. And then in the denominator, now just as a hint, I want to try and get something here that will cancel with the numerator. I'm not going to get a 3x out of this, right? Probably going to get that right there. So that kind of helps me and at least tells me, let's start with 2x times 2x as opposed to 4x times x. Okay? This could only be 3 and 1. Sure be nice if that was positive and this was negative. Let's check it out and see. So 4x squared, 2x minus 6x, that'll give me negative 4, and then negative 3. So that works. And so we do have something that cancels. That was a removable discontinuity. So there would be a hole in the graph at x equals a negative 1/2. That's where the limit is. And the thing now is, I can go ahead and plug that right in and do direct substitution because I'm no longer getting 0 in the denominator. So if I plug in a negative 1/2 up here, I would have a negative 3/2 minus 1. If I put in a negative 1/2 here, I'd get 2 over 2, which is 1. So a negative 1 minus 3. And let's see, if I multiply everything by 2, we got a complex fraction, right? Multiply by 2. So the 2's there will cancel. And what I get is negative 3 minus 2, that's a negative 5. Here I've got a negative 4 times 2, that's a negative 8. And that gives me a positive 5/8. There's my answer. Now how could I check this? If I graph this and get close to a negative 1/2 from the larger side. By the way, when you do direct substitution, we don't really care from which side we're coming at this from, right? Really the only time I care about which side am I coming at this thing from is when there's an asymptote. That means I'm getting 0 in the denominator. I just want to know, does my graph go up to positive infinity or down to negative infinity? But here, I didn't have that. I had a hole in the graph, which means, you know, if you think about what a hole in the graph looks like, we're approaching the same y value from both sides. So once I cancel those, I just got to plug it in and see what I get. All right, so if I wanted to check this on the calculator, I would just graph this original function. We'll clear that. So in the numerator, I've got 6x squared plus x minus 1. And I'm going to divide that by 4x squared minus 4x minus 3. Looks like everything's in there correctly. I hit enter to put it up there, and then we'll graph it. I want to know what's happening as I get close to a negative 1/2 from the larger side. I can see right there, there's a hole in the graph. And so if I hit my trace button and I get close to, oops, right there, see, now we're undefined. So what I want is a negative 0.4999999, a whole bunch of 9s. Okay, I'm getting close to a negative 1/2, a negative 0.5, but from the larger side, so slightly larger than that, I'm not quite as negative. So 0.49999. Hit enter. 0.625, which if you did 5 divided by 8, that's what you would get as a decimal number. Alright, so I feel good about that answer. Alright, so assignment number 6, this is our Wednesday piece. We're doing page 92, we're going to do 4, 7, 11, 13, 15, 19, 23, 27, and 35, and then 39 to 49 on. Alright, so Thursday, we'll review for our test. It's coming up on Monday. Remember, you guys are either taking the test during class or at 6 o'clock in the evening. You have to let me know which one. I'll remind you guys of that on Thursday, but you'll have to email me and let me know, and then I will email the test to your parents. I've got to make sure I've got your parents' email address on file, so you may want to just double check and see if they received an email with the video from me. I sent a video to all the parents. If they got that, then we know that they're getting emails. Okay, if they didn't get it, then we need to know what email to send it to. All right? All right, there it is. I'll see you guys tomorrow on Thursday. All right, bye.